Alright, this is example E3.4 and it has to do with summing forces in a direction that is not one of the Cartesian coordinates. And this example corresponds to example 3.8 in the text. Alright, so here's the problem statement. You can see there is this frictionless bar AB that is fixed in space, and then sliding along this bar is this collar C, and the collar has some weight, and it's also attached to this spring, right? So the spring is attached to the wall over here at point D. And the question then is, if the weight is 240 millimeters from point A and the unstretched spring length is 200 millimeters, and you can see they gave us the spring constant here as well, what is the value of W that must be present, right? And then the second part is, what is the reaction force between the collar and the bar? All right, so we'll go ahead and maybe try to solve that, and then come back and we will work through the problem together. All right, so the general idea here is that we are going to specify the coordinates that are given to us. So we know A and B and D, and then we also know the direction associated with the bar, so that's RAC, I guess RAB, and we know this distance 240 millimeters, so we can also specify point C. And then what we'll do is sum forces in the direction of the bar, because in the direction of the bar we know there can be no reaction force since the collar is frictionless riding on that bar. So that means that in that direction, so the force exerted by the weight plus the force exerted by the spring in the direction of the bar has to be equal to 0. And that should tell us what the weight is. And then they also ask for the reaction. So to get the reaction, we can just sum the forces of the weight and the spring and the reaction force, and those three forces have to sum to 0. And that reaction force had better be perpendicular to the bar, and we can check and make sure that's true. So let's go ahead and derive the governing equations that we need to enter into ease. And once we're sure that we have a complete set, we'll move on to ease and solve them. So yeah, we'll start by defining the coordinates of A, B, and D. That's easy. We know what those are. The position vector that defines the bar is RAB, and that's just B minus A. And then you can see that point C is 240 millimeters from point A in the direction defined by RAB. Right? So that's this equation right here. Right? We know that C is equal to A plus the magnitude of RAC, which is 240 millimeters, and then this is a unit vector that points in the direction of the bar. There's another position vector that corresponds to the spring, so that position vector is RCD, and that's just point D minus point C. And then we can also determine the magnitude of the spring, because we know the spring force, because we know the spring constant, and we know the length, which is the magnitude of RCD minus the unstretched length, so L0. So I know the magnitude and I know the direction, because the direction has to be in the direction of this position vector RCD, so I can also get the vector force FCD. The force due to the weight is something we don't know, but we do know its direction. Its direction has to be vertically downwards. So the weight force is given by this equation, where W is unknown. And then if I want to find W, I just specify that the sum of the forces in the direction RAB has to be 0. Right? So the dot product of the spring force and the unit vector defined by RAB plus the weight, the dot product of the weight and the unit vector defined by RAB have to be equal to 0. And just to make this a little bit easier, let's multiply through by the magnitude of RAB, and I get this equation. And this is a scalar equation that has one unknown, which is the magnitude of W. So that should be enough. There's one more equation if I want the reaction force, but we'll get to that when we get to part B. So let's go ahead and enter these equations into ease. So the first thing I'm going to do is enter the inputs, which include the spring stiffness, the spring's unstretched length, and then the distance from point A to the collar, so the magnitude of RAC. And then I'm going to define these 4 points. So these are defined as vectors, even though they're points, because they have 3 components. So A, B, and D. And you can see according to this figure, A is going to be 0, 60, 240, B is going to be 120, 300, 0, and D is going to be 120, 0, 280. And then I have some position vectors that are of interest. So RAB is the bar, RAC is the distance from A to the collar, and then RCD is the spring, right? So RAB is B minus A. Once I know that, I can use this equation to get point C, and then RCD is just D minus C. Okay, so I can use equations 4 and 5 to define the force from the spring. So here's equation. This is equation having to do with the spring constant and how much the spring is stretched. And then the force from the spring is just the spring constant, and then I have this unit vector, which is the direction. So now I have the spring force, and then finally I can enter my last set of equations. So this is W, which is minus the magnitude of W times the unit vector in the z direction, so vector unit K. And then here I'm just going to specify that the dot product of the spring force in RAB plus the dot product of the weight in RAB has to be equal to 0. And this should solve now, and you can see if we solve, we get that the weight has to be 400 newtons. Okay, so let's see. The next bit is that they want the reaction force. So that's literally just saying that the sum of forces has to be 0. So the force from the spring plus the force of weight plus the reaction force have to sum to 0. And if I want the magnitude of the reaction force, I just use vector mag here, and that will give me the magnitude of the reaction force is 300 newtons. So that's the solution. There's a bunch of things we can do now with the solution. So one thing that we can do is just verify that the reaction force is perpendicular to the bar, right? So if we did our problem right, that should be true, because if it's a frictionless collar, there can be no tangential component, and that's just as easy as checking that the dot product between the reaction force and the position vector defining the bar is equal to 0. So here I'm just doing that check, and you can see that indeed it is equal to 0. Another thing we could do is look at what's the relationship between the weight and the position, right? So we found that if the position is 240 millimeters, the weight had to be like 400 newtons. I would assume if the weight was smaller than that, then this distance would go down, right? So we can build a parametric table to explore that relationship. So here I'm going to go ahead and create a table, and in the table I have W, and I have this magnitude of RAC, and I'm going to put the magnitude of RAC that I specify inside of a dollar if not parametric clause, just so that I can run my table without having to comment this out. And let's go ahead and vary the magnitude of RAC from 0, which would say that the collar is all the way up at point A, to, I don't know, 300, which says that it's slid farther down the bar than it is in the problem statement. And we'll solve the table, and we can make a plot that shows the weight as a function of this distance RAC. And you can see here that, yeah, at 240 millimeters, the weight is 400 newtons, and then as the weight gets smaller, of course, the spring will pull that collar up towards point A, and actually at about 120 millimeters, that's where the weight would be 0. So a zero weight, a massless collar would hang out at 120 millimeters here, and anything below that is actually non-physical, and we should probably remove it from our graph. All right, the last thing we can do is use this problem to illustrate using the $VectorPlot Directive, right? So I might want to make a vector plot that shows a few things, one being the direction of the bar. So I probably want to show, what would it be? I guess RAB is the bar, and we'll plot that. So I'm going to do $VectorPlot, and my first vector is going to be, well, first I got to name it. So name equals, I guess, whatever I want to name it here. And then the first vector I'm going to show is RAB, and I'm going to start RAB from point A because that's where it starts, and I'm going to make it black. And we can go ahead and run this and look at the position of the bar, and that's interesting. But what's really nice now is if I want to add to it, it's easy to add to it. I can go back to the ease file and add more vectors here that I want plotted. So I probably would like to plot the 3 forces that act on the collar. So those 3 forces are, I guess, the weight. So I would plot the weight, and that can be maybe red, and I'm going to start the weight. The origin of the weight's going to be at point C because that's where these things act. Another one is FCD, so that's the spring, so I'll plot FCD. I'm going to start that also at point C, and I'll make it red. And then the reaction force, so I'll start the reaction force at point C, and I'll also make that red. And now when I solve my problem, I should see not only the bar, but also these 3 forces. Right, and you can see that, you know, the weight force is down, which of course it should be. The spring force is going off in the direction of the spring, and then the reaction force is perpendicular to the direction of the bar, which is as it should be as well. So this is a nice way to visualize the problem. It sort of makes it a little bit more real, at least to me, and also illustrates how you use that $VectorPlot directive.